Vale, estoy grabando.
Vale, perfecto. Vale, pues yo creo que podemos empezar.
Vale.
Vale. Okay, so welcome everyone. It is a pleasure to host Eva Miranda from Universitat Politécnica de Catalunya, and there is CRM, I think it's Centro de Recerca Matemática, also. And today she's here to speak about to be or not to be. That is the question. So thank you very much, Eva, and please.
Thank you very much for this invitation that Giovanni did already last year in the middle of the many talks online, and I have been postponing, unfortunately, until now. I'm very happy to give this talk. I'm very happy to be in Como, even if virtually. I hope I can visit soon in person, Giovanni and everyone.
Of course.
And thank you very much for the invitation. I mean, I had to choose one of the results, and I decided to choose everything, which is a bit dangerous, right? About symplectic geometry. Well, everything. I plan to give a kind of panoramic talk about results, mostly in geometry, but also connected to dynamics about in the study of bisymplectic manifolds. And that's why the title, To Be or Not to Be, which was sent as to be or not to be, that is the question twice, which makes sense because it's not to be or not to be squared, which is also a type of singularity I'll be considering. Okay, so Giovanni, people are entering, so I see it on the screen. I don't know if you see it.
Yes, okay. I am letting everybody in. Some people are still like on hold. I don't know why, but
because it takes a while for, well, I don't know. It's a process that takes maybe 2 seconds. It shouldn't take more.
Okay. Some of them, I think they are stuck, but I cannot do anything. Yes.
They should enter again. I don't know.
Yes, maybe they should try to enter again.
Yeah, now there is somebody. Well, I'm going to admit this person myself.
Okay.
Right. Okay, good. So there we go. What I plan to explain lies between symplectic and contact geometry is related to symplectic and contact geometry. Everyone here is familiar, but I'm going to recall very briefly what we need to know to follow the lecture. We just need to remember that symplectic manifolds are manifolds endowed with a form which is closed and non-degenerate. And then we can do things with this form. In particular, we can write what would be the Hamiltonian vector field that satisfies this equation here. And it's important that this non-degeneracy condition and the fact that this form is skew symmetric already tells us that the dimension has to even. So symplectic manifolds are even dimensional manifolds. And as an example to have to bear in mind would be the cotangent bundle having a standard symplectic form, which is the differential of the Liouville one form. This would be like a model example. And indeed, all symplectic manifolds locally look like that. On the other side, we have contact manifolds, which we could think of them as the odd dimensional equivalent, because we also have a kind of form controlling the geometry, rather the kernel of a form. Here we have a one form, which is a contact form, and the condition we require is a condition which is equivalent to non-integrability. And in terms of forms, we have the condition that alpha wedge differential of alpha to the n is a maximal form, a volume form on this manifold, which is going to be odd dimensional. And then instead of Hamiltonian vector fields, well, we can define Hamiltonian vector fields, but before that, we can define, and that's the only one I'll need to consider today, what's called Rep vector fields, because of George Rep. And Rep vector fields are defined by these two equations. So our Rep vector field, once we fix one of these alphas, is given uniquely as the solution to these two equations. So it's in the kernel, if you have alpha, which is a one form, and then you look at the kernel of the differential of alpha, because of this condition, this is one dimensional. So this gives you the direction, and then you choose one of the vectors by normalizing somehow. So you impose that alpha of r equals 1. Then you also have the possibility to use this Rep vector field to define what would be the equivalent of Hamiltonian dynamics in this case. But today I'll talk about essentially red vector fields. And I want to discuss like examples of that are for which maybe you are familiar to, which we could say that the study of geodesic flow gives me a magic box of examples of symplectic and contact structures. So in particular, so if we take the geodesic flow of a Riemannian manifold, this would be a special case of a Hamiltonian flow, okay? And then why it's a special case of a Hamiltonian flow? Because we can use, we can go from the tangent space to the cotangent space, okay? And thinking in the cotangent and transport things to the cotangent space. And then the geodesic flow is just the flow of the Hamiltonian vector field corresponding to this Hamiltonian, where the metric, of course, plays a role, because here you are measuring the norm of P, the metric, okay? Where here we are considering the cotangent bundle, and the symplectic form is the symplectic form that I said that locally all manifolds look like it, which is the differential of the Liouville-1 form. So when we talk about Liouville-1 forms and when we talk about this kind of a structure, indeed we are talking about the structure of physics somehow. So you have some, let's say, special coordinates, which are called position and momentum. Okay, so here you take Q are the position variables on the manifold and P are the momentum. Okay, so here you take as Hamiltonian this Hamiltonian given by the moment. And then, so this gives you a way to relate geodesic flow, which you could, you know, think of coming from Riemannian geometry to symplectic manifolds. And you can also relate it to contact manifolds, because if you consider the spherical tangent bundle, so you take the tangent bundle and you consider vectors of norm one here, you can restrict this this Hamiltonian somehow. The dynamics can be restricted to this spherical tangent bundle, and then the geodesic flow is the red flow of what is called the unit cotangent bundle. Okay, so in a way, geodesics gives us a flow box of examples, and these are geodesics related to a Riemannian manifold. So Khesin-Tabachnikov, they proved long time ago that if you relax the condition of being Riemannian, you get interesting geometrical structures associated. And I'm going to look at these examples, at these kind of structures, because they give us a good motivation for bisymplectic manifolds. So in particular, now if we relax the condition of Riemannian and we consider pseudo-Riemannian manifold, and we consider the set of all geodesics, okay, then we could consider, because the Riemannian manifold is pseudo-Riemannian, we have this fancy notation, like a space-like geodesics, right? Where the G of the velocity is positive, time-like geodesics correspond to negative ones, and like geodesics are the ones that give zero. Okay. Then what Khesin and Tabachnikov did is that they completely give a description of the set of space-like and time-like and light-like geodesics. So what they discovered is that this space of space-like geodesics and time-like geodesics is indeed symplectic, okay? And that the space of light-like geodesics is indeed the boundary of these two symplectic manifolds and has a natural contact structure. Indeed, in their paper, they do more, and they analyze if these two symplectic structures can be glued to a Poisson structure. And this is only valid in dimension 2. What's nice about the Poisson structure in dimension 2, which they completely describe in coordinates adapted to this pseudo-Riemannian structure, is that it gives you an example of what we call bisymplectic manifold. And well, in their paper, they don't talk about this because they don't think that this is a bisymplectic manifold. But then you go to their paper. So this is a natural source of examples. So that's their paper in Advances in Math. And that's the result in which they give this kind of geometrical characterization of the space of geodesics for pseudo-Riemannian metrics. So that's a source of examples, a natural source of examples, where we start from symplectic and contact situation, and then when we relax, instead of considering a Riemannian structure, we consider a pseudo-Riemannian structure. Then naturally we have some singularities appear. Okay, now I'm going to focus on another source of examples, and I'll get back to this example several times in my talk. I'm going to consider the restricted three-body problem. Okay, this is a particular case of the three-body problem. The three-body problem, we have the three bodies attract to each other in similar conditions, and in the restricted three-body problem, right, the conditions are not similar. We have that we assume that two of the bodies play a major role. They are called the primaries, and they move according to Kepler's law. And then the third body, we assume that it's attracted to these primary and secondary planets, but we assume that this body is massless. We can think, for instance, that this is the spacecraft, okay? And we assume that they, well, I mean, we can study several levels of complexity, but let's take the simplest case. Let's assume that things are planar. So this is the restricted planar three-body problem, and let's assume that also that the orbits are circular, because then it could be parabolic, etc. So this would be the restricted circular planar three-body problem, and that would be the kind of picture I'm thinking of. In this case, give me some equations, Eva. Let me convince you that there is a singularity behind in this picture. Well, first, let's write the Hamiltonian. Okay, somebody has done it for us, so we don't have to think. Here, the Hamiltonian will be the total energy of the system, so the kinetic energy and the potential energy. And the potential energy is here and is described in terms of the masses of the primary and the secondary, which are normalized. So one is mu and the other one is 1 minus mu. And here I said that one is the Earth and the other one is the moon. Okay. And then that's the Hamiltonian you consider. Then people who have been working on this, because we are considering the circular case, it's convenient to take a canonical change inspired by polar coordinates. And then one of the persons who studied this problem was Gehee, okay, who considered this additional change, where 0 goes to infinity, and this is what they say, they call people in celestial mechanics, the line at infinity is when x equals 0. Then, so if x equals 0, then r goes to infinity. And after performing this change, we get, because first this is expressed in r, and then we perform this change, and we start from a symplectic object, but after we do the pullback by this change, this object is going to exhibit singularity. So this is a perfect symplectic structure away from 0. And then, of course, when x is 0, it doesn't make sense as such as a the RAM smooth symplectic form. However, its inverse as a Poisson structure makes perfect sense. That's the first observation. And the second observation is that I'll try to convince you today that even if this doesn't make sense, we can change the glasses through which we look at these forms and declare this form here indeed as a generator of the dual of a certain bundle, okay? And then we will have the right to think of this as a smooth form. But let's say it's a smooth form which is not modeled over the cotangent bundle. So we are not going to be thinking of these as sections of wedge 2 of the standard cotangent bundle. We need to replace this cotangent bundle by something else. Okay, and because this has, well, B comes from boundary, okay? I could say that B comes from Barcelona, but this would be too self-centered. Why not? I can do whatever. I could say, well, we call it B because it comes from Barcelona, but this is false because Melrose did it first. And of course, Melrose had been using this language to address problems concerning the index theorem on manifolds with boundary, and B stands for boundary here. Because also this problem, this particular problem, it's one could think of this as a boundary, and people in celestial mechanics think of this as a boundary, Okay, so what's the news here? That there are many ways to look at this form. One way is to think that this is smooth away from x equal to 0, and then you don't want to know anything else about x equal to 0. And a different perspective is, let's have a look at x equal to 0. Can we make some sense of this? Can we describe something about the geometry or dynamics of what's going on at x equal to 0? And that's our point. Our point of view is, do not neglect this infinity, but we want in a way to compactify this example. And then the price of compactifying this example is that the manifold, the geometry, cannot be standard symplectic. It has to be something else. So that's one of our motivating examples. And let's say, for the same price, we may look at forms that have different exponents. So we want to look, that's not a definition, that's a first approach. We would like to understand forms of this sort, and which locally look like this. And this is what we call BM symplectic. We have a formal definition that will come later. And then we would also like to look some kind of, let's say, dual forms, which could be called M-folded. And indeed, these forms are already considered, were already considered in the literature a long time ago. Okay, and while this would be the context of singular symplectic manifolds, and then you could play a similar game as we did in the motivating example, that to get contact structures, you restrict to an hypersurface. Okay, can any hypersurface is any hypersurface good to restrict this structure? No, you need to have what is called a Liouville vector field transverse. But okay, once you have it, you have an induced contact structure. So what happens if your initial symplectic form has a singularity? Well, what we expect is that this contact structure may inherit this singularity too. How are these singularities? So concerning this example, I would like to explain a little bit more. That would be the setup, but I would like to explain the connection to the first image that I saw, where we have, well, if I consider contact structures, then what's relevant are going to be the red vector field. So I want to describe a little bit more why geometry is important in the restricted three-body problem. So one of the, I want to do this restriction to get this contact structure, but I need to work a little bit harder, because the previous Hamiltonian that I was describing here, which was sufficient to show that this structure would be singular, depends on time. And this is not nice. So a way not to make it dependent on time is to change the rotating coordinates. And then the Hamiltonian of the problem looks like this. And what's interesting is that if you look at the singularities at the critical points of this Hamiltonian, you get the famous Lagrange points that have been famous because NASA is sending now things to the second Lagrange point. So then you know that, well, they have to be important. And they are important because they are equilibrium points. Then you don't spend so much fuel getting there. So they are really used nowadays, as we saw in NASA well, just recently. I think it's 1 month ago. Okay. So one of the natural questions when you are considering problems in celestial mechanics is, okay, if you throw your satellite, will it go back to the initial point? That's desirable. That's what mathematicians we call periodic orbits, right? So can you study periodic orbits? And of course, the point of view in practice usually is using methods which are based on KAM theory, but very basic methods. That's what they usually do, right? So what they call perturbative methods. But the question is, can we apply some method which is really, really geometrical here? And indeed, yes, we can. One interesting thing is that if you consider this Hamiltonian and you take a fixed energy level, okay, you can analyze the connected components. And the number of connected components depends on the fact if the satellite stays close to the Earth, to the Moon, or is far away. Then you have you have these three connected components, right? that's sort of interesting. So that's a little bit the topology, right, of the restricted three-body problem. Okay, and then now from a geometrical point of view, what we want to know is if these manifolds inherit some contact structure. What's usually done, people in celestial mechanics usually do, is that they consider a regularization procedure which was thought by Moser, which indeed the outcome of this procedure in this problem is that it compactifies these connected components. Okay, so they are then as manifolds diffeomorphic once compactified to the real projective space. Now you want to understand more about their geometry. So you want to understand, can I describe some kind of contact structure? Okay, indeed, well, here, I mean, there are funny things going on. For instance, in this connected component, this is diffeomorphic to this connected sum. That's something interesting. So you totally understand the geometry. And what's more, you understand that you have a certain contact form. And this was discovered by Albers, Frauenfelder, Van Coert, and Paternay, okay, in which indeed they described this structure completely, and they discovered that it's a tight contact structure. Why is this important? Okay, coming back to the question of, will my satellite come back to me, or what are the periodic orbits of the satellite? This connects to Weinstein conjecture. Weinstein conjecture was coined by Alan Weinstein initially with a particular contact structure coming from restrictions on R2n, but now is considered on any contact manifold. Okay, and his conjecture is that the red vector field on a contact compact manifold admits at least a periodic orbit. I could say that while this was proved completely by Taubes, there has been a lot of progress, especially in the last couple of years. Now people start thinking that that's not the question. It's not about existence of one, but it's existence of two or infinity. That's the current status of new versions of the conjecture. But using the fact that on three-dimensional manifolds, we have that any compact contact manifold admits a periodic orbit, because of putting everything together in this restricted three-body problem and considering this Moser transformation that compactifies, and looking at the dimension of your restriction, which is 3, Albers, Frauenfelder, and Van Coert observed that for any value of C, okay, so if you take a level of energy below the first Lagrange point, okay, the regularized planar circular restricted three-body problem is going to have a closed orbit with energy C. If you apply the last techniques, maybe you can say more about the number of periodic orbits. Indeed, like, it wouldn't be surprising to get a lot of periodic orbits, infinite number of periodic orbits. So that's one of the questions that it's on the intersection of dynamics and geometry, and that it's one of the focuses in contact geometry nowadays. So going back to our business of, you know, putting structures and singular structures and thinking of these singular structures as some kind of compactification of your initial models. Now what makes sense is, do you have singularities in the contact structure? And can you apply Weinstein conjecture for these singular contact manifolds? So would you get a similar result? We will go back to this motivating example, but by now a little bit, if I have to convince you, why should we consider these singular manifolds? I could do it with giving you 5 reasons. First one, yeah, we saw two-dimensional space of geodesics on a pseudo-Riemannian manifold singular. We saw this. That would be a first reason, because some non-compact symplectic manifolds can be compactified, and the price to pay is that then we have singular symplectic manifolds. And these singularities appear on regularization transformation in celestial mechanics. Of course, then there is the initial motivation of Melrose. They model certain manifolds with boundary. So whatever happens close to the boundary, we need to describe. It's good, it's handy to put to consider this singular structure. And my favorite one, which is the why not reason. All right, why not? Why shouldn't we consider these singular structures? This is would be the natural generalization of this. And another source of examples that has some physical meaning, and today is especially a good example to give, right? Because we just knew, like at 12, that Dennis Sullivan got the Abel Prize, right? So I feel obliged to say something about this. And one of his contributions was to relate the topology to fluid. So it was to intermingle dynamics and topology. And today I'll comment one of his contributions. So for that, I need to introduce what are Euler equations. So imagine that now, instead of I consider dynamics of a fluid flow, and I'm going to assume that the fluid is non-viscous. So I'm not considering Navier-Stokes problem that could give me a lot of money. I'm considering the case in which I don't have viscosity. So the problem is unviscid, okay? And I am assuming that it's incompressible fluid flow. So these would be the equations that, okay, these equations, usually you can make sense of them on any Riemannian manifold. Originally, this is the language used on R3, okay, by considering the standard Euclidean metric. But indeed, the Euler equations make sense on any Riemannian manifold. And sometimes it's convenient to consider them. And if we look at solutions of this equation, a special class of solutions is the simplest possible case, which is the case in which this term is zero. If this term is zero, it means we are considering stationary solutions of the Euler equations. Among the solutions which are stationary, there are the ones given by Beltrami fields in dimension 3. Beltrami fields are fields, vector fields, which satisfy that the curl, sorry, it's proportional to the vector, and that they are divergence free. The condition, the physical condition of divergence free is related to the fact that the flow will preserve the volume. Okay. These are stationary solutions with constant Bernoulli function, and the Bernoulli function is related to the pressure. Okay, I went very quick here, but I didn't say that, well, this is a PD, and the unknowns here is indeed the evolution of the system, X, and also the pressure, okay? And then the Bernoulli function is described in terms of the pressure and the metric, because this equation makes sense for any metric, and then here you can write the covariant derivative. Okay, now I want to talk about Dennis Sullivan, who won the Abel Prize today. So in order to talk about Dennis Sullivan and his contributions, I have to relate problems in dynamics to problems with topology, right? So we have here a problem in dynamics, and now what we do is to associate to it a problem in topology. I'm going to consider one form, and this one form, I describe it as the contraction with the metric of this vector field, okay? Then if I consider the volume, then it's possible to rewrite these equations in the dual language of forms, so much more geometrical. And then the stationary equations, I wouldn't have this term, and this would be translated in these two equations, okay? These two equations reminds us of the first slide, where I was talking about contact structures, okay? And I was talking about symplectic structures. And well, what's fantastic, and I'm going to unveil it now, is that this one form is indeed a contact, defines a contact structure. Why is so? The Beltrami equation, just by dualizing it with a metric, can be written in these terms. And then the condition of being contact structure in dimension 3 is equivalent to the fact that alpha wedge the alpha is a volume form. But if you write it down, right, alpha wedge the alpha, because the Beltrami equation reads like that, reads as this term. This as alpha wedge the contraction with mu. Then you take your favorite coordinates, you can check that this is positive, that this is non-vanishing. And the F is positive, of course. So this means that alpha is a contact form. Furthermore, what is the red vector field? Well, you just need to contract. What I want to convince you is that the direction of the red vector field is the same as the solutions of the fluids. Okay, and that's a computation. You just contract with x differential of alpha, and you get 0. This means that it's in the same direction. So it would be cool if this Beltrami field x, okay, would be also a red vector field. And this is almost true. So it has the same direction, but maybe it's not the same vector field. You need to maybe shorten it up a little bit, normalize it. You need to normalize it with the metric. So indeed, you can always reparameterize such that this is the red vector field by considering this function. And well, this idea, this was proved indeed by Ednar and Rice, but there are very nice talks that are recorded on the Einstein chair, where you can find a talk of Dennis Sullivan, where he was already writing this kind of equation. So in a way, Dennis Sullivan already was suggesting that you had such a correspondence between fluid dynamics and contact geometry. But this was really proved by Ednar and Rice. So Ednar and Rice proved that there is a one-to-one correspondence between Beltrami fields and contact structures. Important to say they proved this in dimension 3, but this holds in any dimension. That's something that we could prove in any other dimension with Robert and Daniel. And you can extend this correspondence also on manifolds with cylindrical ends. So you think of manifolds with boundary, and to get singular contact structures. So we could say that Beltrami fields, and if you want, the one who got the Abel Prize today, gives us good examples of big contact structures using Beltrami fields. Okay, because with this correspondence, Beltrami fields, we have a magic mirror, and with this correspondence, Beltrami fields are indeed exactly become the red vector field after reparameterization with this metric. Okay, so you have like a kind of dictionary between geometry and fluids that works well at the level of Beltrami fields. So first level of difficulty, remember that Beltrami fields would be solution of these fluid equations when they are stationary, right? So we are in a concrete case, if you want, but which is very rich. It tells you that you have a dictionary between contact geometry and these stationary solutions of Euler equations. And this observation, I mean, this theorem was proved by Ednar and Rice, and they used it to prove the existence of periodic orbits for Beltrami vector fields. At the moment in which they wrote their paper, the proof of Taubes was still not there, but they proved it for the 3-sphere. And the proof holds whenever Weinstein conjecture is true for contact manifolds, then you just need to cross the mirror and apply the result to prove existence of periodic orbits for Beltrami vector fields. Indeed, at the end of my talk, if I have time, I'll use this mirror again to prove the existence of singular periodic orbits. So now, well, I have been talking about motivation. I think motivation is important, but it's time to get real. I want to, consider this, formalize this idea of singular structures. A way to do it is to do a graffiti over my previous picture, right? And put a V everywhere and say, it works the same. Well, this is not very professional, but essentially that's what I'm going to do. I mean, I'm going to formalize why you can just, these conventions work very well when you extend them to the singular realm, for which I need to be able to look at these forms as smooth forms. Or for that, I need to make some kind of F. So, well, that's a nice picture of Como that I'm missing, right? Of Como Lake. So let's zoom in and out of contact geometry. First of all, what's the definition of Poisson structure? I have said Poisson at the beginning of my talk. If you don't like Poisson manifolds, it's okay. This is going to be one slide. Then I'll go back to forms. But a way to look at these singular structures is to see that I have Poisson structure, which I could think of as a bivector field, so a kind of dual to a form, okay? And I'm assuming that I have an even dimensional Poisson vector, Poisson manifold, okay? Well, here I could assume that it's oriented or not, it's not important, okay? But what I need to assume is that this mapping is transverse to the zero section. The mapping that sends the point to pi n, okay, is transverse to the zero section. If I assume this transversality, under this transversality assumption, then what happens is that the set of points where pi n is equal to 0, right, because of the transversality, this is going to be a smooth manifold. And this smooth manifold is what we call the critical hypersurface. So if you try to do this experiment and you take your favorite symplectic structure, now you dualize, so you have a bivector field. Then what happens is that in the symplectic case, pi n, the dual of omega, because omega is non-degenerate, is always positive, cannot vanish. So what is the next case, if I consider symplectic case, is the case in which this vanishes at some point, okay? And here we can get very sophisticated. We can consider other kind of singularities. We could consider, instead of putting this transversality, we could take the point of view of Golubitsky with singularity theory and consider indeed stratification of singularities. This has been by several people, including Melinda Lanius and Cavalcanti, Classe, Witte, and also my former student Arnaud Planas. Okay, and also Jeff Scott. I forgot to put it here, because here one of the singularities you may consider is take a certain, let's say, consider the same set as the big case, okay? But then impose that you have singularities up to order n. And this is what you call BM singularities. They were studied by Jeff Scott. In this case, if you like simple Poisson manifolds, if you don't, it's okay. In 2 slides, we will be out. Then one thing you worry about is a symplectic foliation. In this case, what happens is that you have a symplectic foliations whose leaves of maximal rank coincide with the dimension of the manifold, and they are dense, okay? And away from that, you have in the B case, Z is an hypersurface, and it's foliated by symplectic leaves of codimension 1. So this set is an hypersurface, but it's also a Poisson submanifold. In the language of geometry, this submanifold indeed is a cos-symplectic manifold. In terms of examples, if we look at the theory of Poisson geometry, first sort of examples were considered by Olga Radko, who passed away last year, unfortunately, whose thesis was about classifying these structures on surfaces from the point of view of Poisson geometry. Okay, from the point of view of foliation theory, we have tons of examples, because whenever we have a codimension 1 foliation such that it admits a transverse vector field, which preserves this symplectic foliation. So let's assume we have a codimension 1 symplectic foliation, and let's assume, and that imposes topological obstruction. Let's assume that we have a vector field which is transverse to the symplectic foliation, okay, and preserves the Poisson structure on them. So we could think of this vector field as a Poisson vector field. Then in this case, when we consider that's n, so that's the same, I could think that I have a corank 1 Poisson manifold, or that I have a codimension 1 symplectic foliation, okay? And then I consider the product, for instance, with S1, if I want to make it compact. Then this guy here, it's a B Poisson manifold, whenever this F vanishes linearly, if I have this condition of transversality. So I have a close relation between these objects and foliations in codimension 1. Indeed, I have a deeper relation between foliations of codimension 1, because as I said, Z, the critical set, is foliated by symplectic leaves of codimension 1. But this foliation is extremely easy. If you assume that one of the leaves is compact, then just by taking the flow of this transverse vector field, you can just transport this symplectic structure, and what you obtain, it's a symplectic mapping torus. So that's the kind of structure you get. You get a cos-symplectic manifold, and this cos-symplectic manifold is just a symplectic mapping torus. One of the results that Giovanni did a long time ago was to look at the case in which you also have a toric action on these cos-symplectic manifolds. And then he proved that you have the same result, but you have indeed a toric mapping, symplectic mapping torus. So you can do this equivariant as you want. So it's time to change my glasses. So I have my new glasses. I mean, when you are old, you have to have a pair of glasses, right? So these are my other glasses. These are the glasses I use to look close at emails and at things that I get. These are the glasses I use to look close to things. So these are my big glasses. Of course, they are supposed to be very ugly, right? Because they are the big glasses. They are not the ones you use. So, but they are convenient. So these are the ones I use to give my talk. And if I want to look at the objects, I put some new glasses. These are the big glasses. Let me explain what I mean by big glasses. What I'm going to do now is if you didn't like Poisson geometry, no problems. What I'm going to do is to associate to this Poisson structure a symplectic form with singularities, but I will not see the singularities anymore, because with my new glasses, the singularities will be on some bundle associated to the problem. Let me explain more clear. Let's consider the big case, okay? I'm going to construct a new bundle just by considering the set of vector fields. Let's consider a manifold, let's consider an hypersurface, and let's consider the set of vector fields that are tangent to this hypersurface, okay? This set of vector fields, which are tangent to the hypersurface, indeed can be seen as sections of a new bundle. And that's exactly the B-tangent bundle. Here I do this very formally. So I define the B-tangent bundle by defining their sections. This is something that only people in algebraic geometry can do. Of course, this was initially thought by Serre in the analytic case, and it works well, and it's a handy condition. So when you consider this set, you can associate a bundle if you have the condition of this set being a projective module. Okay, so you have some kind of generators of this set. So that's how you define a new bundle. And this new bundle is the B-tangent bundle. What does the B-tangent do for you? The B-tangent, what it does for you is to put this singularity on the bundle, so you don't see it anymore, okay? Once you have the B-tangent bundle, you can dualize, and you have the B-cotangent bundle. And then how do you formalize the idea of singular forms? Now, singular forms are just going to be sections of this new bundle, okay? So a form of degree P is going to be sections of exterior products, okay, of the B-cotangent bundle. And the B-cotangent bundle is just the dual of the B-tangent bundle that I have created just by calling Serre and asking him for help to say, look, I want to construct a bundle having these sections. And then he says, it's okay, you just need to check that it's projective. And then you have that this proves that such a bundle exists. Once you have this bundle, you can just you can just do symplectic geometry over the new bundle. That's essentially the big trick. Well, this bundle indeed was used by Melrose, and Melrose proved that there is a close relation between forms, sections of this new bundle, okay, and the RAM forms. And these forms, indeed, you can construct a cohomology, what is called the B cohomology, and this is closely related to the RAM cohomology. And you have this formula, which was proved by Matteo and Melrose. So what is a B-symplectic form with my new glasses? With my new glasses, a B-symplectic form Now I look at my glasses and I don't see the singularity anymore because the singularity is embedded on this bundle. Okay, so with my new big glasses, a B-symplectic form is a closed non-degenerate B form of degree 2. And once I realized about this, and this took us a while because we were dealing with these forms from the Poisson perspective, and it's better to think of them as singular forms, as doing symplectic geometry over a new bundle. Okay, once you realize about this, what's good about B-symplectic geometry? Many things. One thing is that the path method works very well. So you can prove, for instance, you have a Biedermuth theorem. You can prove semi-local forms, etc. And how do you formalize this idea of contact structure with singularity? It's the same. You copy the same definition of my first slide, okay? And then you just assume that alpha is a one form of this new complex. Once you realize about this, everything is very easy. Well, there are some complications because it's not that once, I mean, you are doing somehow symplectic geometry over this bundle, but if you want to read the geometry, you need to translate things to the standard tangent bundle, right? So you get some, let's say, the outcome of this is that essentially you get some new invariants, which are Poisson invariants, but you can indeed classify quite a lot these objects. And that's something that you cannot do in general for a general Poisson manifold. So a B Poisson manifold is the same, of course, as a B-symplectic manifold. One thing you can do, just to give some examples, would be to understand and classify integrable systems on this manifold. Then it's convenient to add to the set of admissible functions, functions which have a logarithm term. That's necessary. Otherwise, the tangent space to this manifold doesn't have enough dimension. And then you can classify, for instance, you can try to understand integrable systems there, and you can try to construct action angle coordinates. That's something I did with my former student, Anna Khesin-Tabachnikov, who is well known because she's a world champion. She got a gold medal for cycling, not for B-symplectic geometry. But in any case, it's good propaganda for B-symplectic geometry. And Jeff Scott. We proved that we have some kind of action angle coordinates also for these manifolds. So in particular, we could think that an integrable system is exactly like a cotangent lift, what we call a twisted cotangent lift, as it happens in standard symplectic geometry. Another thing you can do is to understand and completely classify toric manifolds. And you can do this in the same way we do in the symplectic case, which is we associate a Del-Sum polytope. The thing is that this Del-Sum polytope, because we are obliged to consider moment maps, we have logarithmic components, this Del-Sum polytope goes to infinity, so we need to compactify it. And once we understand that we need to compactify it, then we completely can classify these manifolds. And these manifolds are of two types. This here, you have a picture of a symplectic manifold where the critical set is the red curve, where this is singular, okay? And here you have the case of the torus. And in these two structures, this is what we call the B torus and the B sphere. And then what you know is that the classification, you have any B symplectic toric manifold has to be of these two types. It's either a product of a B torus with X, or it's a combination of a product with a B sphere, and then maybe you have some symplectic cutting that happens away from the critical set. Once you understand the classification of toric manifolds, which would be, of course, an example of integrable systems, but a global classification, one thing you can do is to quantize. So one application, and this is very recent, this was on the arXiv a couple of weeks ago, is to understand that how we can quantize these manifolds that go at infinity, just by looking at the Del-Sum polytope. And one conclusion and one interesting observation that I'm going to give as a fact is that in the symplectic case, the integer points of the polytope correspond to Bohr-Sommerfeld leaves. Okay, and indeed, well, that's the landscape of geometric quantization. I'm too late in my talk to give details, but essentially geometric quantization is something that you try to, you know, make some sense of the quantum models. So what you expect is that if you start with a compact manifold, you get a finite dimensional model. What happens on the B case is that you have a compact manifold, but when you count the number of Bohr-Sommerfeld leaves, you get infinite of them. So if we want to copy geometric quantization for these manifolds, we need to be a little bit more original. One thing we need to do, this is an example, you take the B sphere, so you take the sphere with this singularity, that's your moment map. And here you have this in red and blue. Why red and blue? Because I'm in Barcelona. You have what are the Bohr-Sommerfeld leaves. If you count them, you get infinity. Then you don't have a finite model. But if you count them carefully, then you get a finite model. Count them carefully means to associate a sign depending on the orientation of the symplectic leaf where you are, and then consider this addition of Bohr-Sommerfeld leaves with sign. This very basic and naive idea works out. And that's what we proved with Pau Mir and Jonathan Weitzman. And this is a paper on the archive that the idea is what I have explained, right? But to formalize it down, what we do is first to prove that geometric quantization coincides with formal geometric quantization, and then to identify these Bohr-Sommerfeld leaves by looking at the polyton. Essentially, the final outcome is that you can quantize these objects just by counting the Bohr-Sommerfeld leaves carefully with sign. That's the message. Okay, one thing you can do, I have like 5 minutes to the end of my talk. I realize I put too many things in this panorama talk. But one interesting thing is to understand how different are these objects from symplectic manifolds. That's a natural question. Before we started to work on bisymplectic manifolds, people had been working on folded symplectic manifolds. And indeed, in that case, the Delsan theorem, it's really a kind, you can associate a kind of origami template of Delsan polytopes. This was done by Anarita Pires in her thesis long time ago. So it would be good to understand if these boxes are really different or we are ticking the same box once and again. Let's think. You can try to prove the Darboux theorem. Indeed, it works well, symplectic manifold, bisymplectic manifolds, folded symplectic manifolds. Who did it? Martinet already, long time ago. We have a Delsan and convexity theorem in symplectic case. For bisymplectic manifolds, yes, we proved this. Also, besides the Delsan theorem, the convexity theorem for torus actions. And you also have Delsan type theorems in the folded case. We have actional coordinates. Also, in this case, also in the folded case, this is something we did with Robert Carroll. So we have the same kind of results. Is this the same? Let's look at examples. Well, let's look at the simplest possible example. If we have a surface, this surface is going to be everything we want. It's going to be symplectic, folded symplectic, and orientable or not, doesn't matter. It's going to be bisymplectic. I mean, if it's non-orientable, of course, it cannot be symplectic, but it can be bisymplectic. That's a surprise. For CP2, indeed, we know CP2 is symplectic. Oh my God, of course, CP2 is symplectic. We know CP2 is folded symplectic because it's a four-dimensional manifold. Okay, like, and then indeed we can exhibit explicitly the folded structure. Okay, and but for four-dimensional manifolds, it was proved by Anna Canas that any four-dimensional manifold admits a folded symplectic structure. And in higher dimensions, it's understood what are the constraints. What's very funny is that CP2 is not a symplectic manifold. The reason is that there is no form in the second cohomology group. Okay, we need to have a form such that the square is 0. And this doesn't work well in CP2. So CP2 is not. We need to have a connected sum of CP2 with something else, with other CP2s, with different orientation in order to be able to have this bisymplectic structure. This was proved by Cavalcanti. In S4, of course, you cannot have a symplectic structure. We have a basic proof of this, right? The second cohomology class, I mean, we know that the fact of having a symplectic structure gives a non-vanishing class in H2. This same proof, but in big homology, is going to tell you that this guy is not bisymplectic, but it's folded symplectic because it's 4-dimensional, and therefore, because of Anna-Canas, it admits a folded structure. So there's something funny going on. It's not exactly the same. And how they are related, this is something we discovered quite late in the game with Victor and Jonathan. We proved that we can desingularize these structures. So given a BM symplectic structure, we can desingularize it. And the type of desingularization you get depends on the fact that M is odd or even. If M is even, then you can desingularize this as a symplectic manifold. So then, if the title of my talk was to be or not to be twice, so to be or not to be squared, if I consider a B2 structure, then the desingularization is going to be symplectic. So whatever you know in symplectic geometry, you can try to apply it here, right? Of course, you need to go back. That's non-trivial, but it's a first step to understand. At least the topological abstractions that you have are going to apply to your initial manifold. And if it's odd, then the desingularization gives you a family of folded symplectic forms. That's quite a powerful tool. And how do you do it? Essentially, you apply your general principle in life, which is if you don't like something, just change it. And in mathematics, maybe you don't like this singularity, so you try to eat this by integration. I'm doing here the even dimensional case, just by trying to integrate this to a function that has these properties. And then what you do is to transform this as a differential of f epsilon. Because of this change of sign, you can only do this game in the even dimensional case, okay? Because then the integral is going to be odd. And then in the odd case, there's no way you can find this replacement. You'll have to multiply with some other function that has to vanish. Then you get the folded case. That's the idea of the proof. Indeed, once you do this change, you get this form, and then you check that it's symplectic. And that's a strong tool. And towards the end of my talk, and I wanted to go back to the initial example just to finish. Can I take 2 minutes, Giovanni?
Of course, yes. Furthermore, you started a little later, so you're still within 60 minutes, definitely. Okay, good. So just to, I mean, I had too many things to explain, but let me choose just one, go back to the initial motivating example. Now I want to attack the Weinstein conjecture. So I tried to show you that many things in symplectic geometry hold. In the bisymplectic case, what is the difference? You have this kind of desingularization, you have del-sum games, blah, blah, you have quantization. What happens with the contact structures? Can you prove Weinstein conjecture for these guys? Well, one interesting and surprising result is that you have a very strong result. So if you have a 3-dimensional manifold and your critical hypersurface is closed, you get for free, in the 3-dimensional case, infinite many periodic orbits on Z. So not only one, you get infinite. And the proof is very simple. The key point of the proof is highlighted in red. The proof is that the red vector field, indeed, when you the red vector field has to be tangent to this critical hypersurface, you are now odd-dimensional, and the critical hypersurface is 2-dimensional, and it's a symplectic manifold. And the red vector field, it's tangent to this symplectic manifold, and indeed, it's Hamiltonian. And that's the whole point. You have 2-dimensional manifold with a Hamiltonian, and you get infinite number of periodic orbits. That's the proof. That's very simple. But there are examples. Now, what about outside Z? You have examples where you have none of them. One thing we did is to understand that in the case in which the
the contact manifold is over twisted. You can adapt some techniques of Hofer, which I will not say, and you can prove that you have periodic orbits. But I will not mention this result of Hofer because I have no time. But one application to the initial example of the restricted three-body problem, and that's a surprising new result, is that, well, because of this theorem I just said, that in the three-dimensional case, when you restrict it to the critical set, if the critical set is compact, then you get infinite number of periodic orbits. Well, let's try to adapt this idea to the restricted three-body problem. What happens, unfortunately, is that there the critical set is no longer compact. So you cannot apply straight away the former result, but you can compute it. And that's what we did. And the main idea is that then this critical set is a symplectic manifold and you have an actual Hamiltonian. And what happens is that you have a cylinder. And this cylinder is foliated by periodic orbits. So we were able to prove that there exists a new family of periodic orbits on the restricted three-body problem. And that's one of the things we proved. Then we proved this thing of Hofer, which I'm skipping. And what's deeper is, okay, what about this kind of orbits? These would be orbits that also have singularities themselves. These orbits appear in this bridge, which is on the rear of my slides, which is I cannot pronounce it correctly. Giovanni will help me because he has been in Germany many times. He has been living in Germany. He's almost German. So what's the name of this bridge? It's Roche, what's the name? Roche, well, it's a bridge. You don't know this, but it's a bridge in Germany. Where
I don't know where the bridge is.
Rochebrücke, but I don't want to pronounce it because it's like something like Rochebrücke. I should have practiced this. Okay, but what's nice about this? Thank you, Giovanni. What's nice about this is that the reflection has some critical points there. So that would be a new type of Weinstein conjecture where you consider these singularities. And I will not explain, I had more slides, but I will stop here. But these singularities are related to escape trajectories in celestial mechanics. So how can you look for these singularities? Well, one option would be to try to construct some kind of Floer homology to be able to fish this singular structures or some kind of contact homology. And well, I mean, I'm going to skip this, and that's in the pipeline. That's a lot of things that we want to do. But also, let me finish with this image, which is when we try to apply, we did something about escape singularities, but we did it theoretically, and it doesn't apply well to the restricted three-body problem, because we wanted to prove something that Poincaré observed, that on the restricted three-body problem, when you get close to infinity, you have an infinite number of periodic orbits that go there, and therefore you expect to have these singular orbits. However, we had applied some result of Uhlenbeck, and this is for which we use this mirror between contact geometry and fluid dynamics. But this made us a little bit Superman, right? But then you go back to the restricted three-body problem, where you have your equations and so on, and you try to check that this fulfills your hypothesis. And then you realize that, well, you are no longer Superman. You are a standard. You look yourself in the mirror and you lost your superpowers, right? So we were able to prove the existence of some singular orbits, which we call escape orbits, but in general, in an abstract form, whenever some conditions are fulfilled. And we were not able to prove that this applies to the restricted three-body problem. I mean, this is some work that we did together with Cedric, who's connected with Daniel. I could say maybe this is me and this is Cedric and this is Daniel. I don't know. One of them is Superman. I don't know, whatever. So let me finish my talk here, and thank you very much for your attention.